Welcome to Lesson 5.1 and 5.2. We are going to learn how to verify triangles, circumcenters, orthocenters, incenters, and centroids. For our vocabulary, we have the perpendicular bisector, concurrent, which refers to concurrent lines that we learned about in Chapter 1, I believe it was, circumscribed, altitudes, angle bisectors, and medians. Our first theorem is Theorem 5.1.1. A point lies on the perpendicular bisector of a segment if and only if it is equidistant from its endpoints. The point will be equidistant regardless of where point P lies on the perpendicular bisector. So let's take a look at this. We have a segment AB, and we have a perpendicular bisector, which means that segment AM and segment BM are congruent to each other. So we've already learned this before. And we also know that we have a perpendicular bisector. We create 90-degree angles. Point P lies on the perpendicular bisector of segment AB if and only if AP is equal to BP. So we know that this point is on this bisector, MP, if and only if these two segments, AP and BP, are the same length. Our first type of triangle center that we're going to learn about is the circumcenter of a triangle. The circumcenter is 3 perpendicular bisectors. So that's why we were just talking about perpendicular bisectors to help us to remember what that means. So to make or create a circumcenter of a triangle, which will be the point where 3 lines are concurrent, we take each segment of the triangle and we make a perpendicular bisector. You can do this with your compass as a construction. You can also do this with your protractor by measuring the segment length, dividing it in half, and then drawing a line that is 90 degrees. If you need help with this, I encourage you to go to either Math is Fun or Math Open Reference, the websites we have used before, to watch animated drawings of these constructions. Once we've drawn the 3 perpendicular bisectors of the sides, you'll find a point where they all meet, and that is the point of concurrency, and that will be the circumcenter of this triangle. Theorem 5.1.2 is the circumcenter theorem. The perpendicular bisectors of the sides of a triangle are concurrent at the circumcenter, the point that is equidistant from its vertices. So in this drawing that we have here, we have segment CX, and CX is equal to CZ. So CX and CZ are the same length. CX and CY are also the same length, and CZ and CY are the same length. So any point on a segment's perpendicular bisector will be equidistant from its endpoints at the vertices. So this is something you should have in your notes. Construction 10. Using your protractor, draw the perpendicular bisector of each side of the triangle. So what you want to do is make a perpendicular bisector of at least two sides of your triangle. And if it is accurate as a construction, you will actually have your concurrency point. And if you were to measure from the concurrency point to the edge of each vertice, so if you were to measure from point C to Z, C to Y, or C to X, they will be the same length. We have a definition, and this is the definition of altitude. Now, you've learned about altitude before in Algebra 1. An altitude of a triangle is a segment that extends from a vertex and is perpendicular to the line containing the opposite side. In some cases in triangles, that'll be inside the triangle. So, for this triangle, you'll see that the altitude goes from the vertex to the other side, the opposite side of the triangle, creating a 90-degree angle. In a right triangle, the altitude will actually be the side of the triangle. And if the triangle were flipped, it could actually also be the other side. When you have obtuse triangles, you'll often find that the altitude will be on the outside of the triangle, and what you'll have to do is draw a line that extends at the base of the triangle so that you can drop the altitude. Our next definition for centers of triangles is orthocenter, and the orthocenter uses three altitudes. The altitudes go from the vertex to the opposite side at a 90-degree angle. So theorem 5.1.3, the lines that contain the altitudes of a triangle are concurrent at the orthocenter. So, in this triangle we have the orthocenter V. We have an altitude PT that meets the opposite side from the vertex at a 90-degree angle. You have the altitude RS, and you have the altitude QU. These can be a little difficult to construct. You might have more success drawing with a protractor, but give constructions a try and use the websites I talked to you about. Definition: angle bisectors. So an angle bisector is a ray that is in the interior of an angle and forms congruent adjacent angles. So in this case, we have an angle bisector of BD, which is dividing the angle ABC in half. It creates two angles, angle 1 and angle 2, which are congruent to each other. And if we draw a line on the angle a point on the angle bisector, label it P, the distance from P to AB, if drawn in a perpendicular, will be the same length as the distance from P to BC. So EP will be congruent to PF. A point lies, theorem 5.2.1, a point lies on the bisector of an angle if and only if it is equidistant from its sides. So same drawing that we just saw, and they're basically stating that EP must be congruent to FP for this to be true, for a point to actually be on this bisector. And point P can be anywhere along BD for this to be true. Theorem 5.2.2, the Incenter theorem. So we use angle bisectors to draw the incenter of our triangle. So the incenter, we have incenter I in this triangle. The triangle's angle bisectors are concurrent at the incenter. this point is equidistant from each side of the triangle. So in our previous triangles, we had a triangle where the points were equidistant from the vertices, but in this one, the point will be equidistant from the sides at a 90-degree angle. So we've drawn 3 angle bisectors. Angle ZXY has been bisected, angle ZYX has been bisected, and angle YZX has been bisected. The lines meet at point I, and BI is congruent to CI is congruent to AI. Construction 11. Using your protractor, draw the angle bisectors of each angle of a triangle. With your protractor, draw a perpendicular from the incenter to the side of the triangle. So you bisect the angles, and then you take the point of concurrency and you draw a perpendicular to the side of the triangle. You can use your compass to measure and draw the circle if you want to, using this segment IS as your radius. Definition: median. The median of a triangle is a segment extending from a vertex to the midpoint of the opposite side. This can be confusing when we're thinking now of altitudes and angle bisectors and perpendicular bisectors. But the median goes from the vertex to the middle of the opposite side. This is fairly easy to draw. You'll get a clear point of concurrency in this triangle. It's point G. That brings us to theorem 5.2.3, which is the centroid theorem. So we use medians to draw the centroid. And there's a special relationship that's created with the centroid. As an example, if we take segment AX here, the distance from A to G will be 2/3 the distance from G to X. The distance from B to G will be 2/3 the distance from G to Y. And the distance from C to G will be 2/3 the distance from G to X. So right here below the triangle, you can see the actual statement for that. Let me start with CG will be 2/3 of CZ. What this does is create a length with a 2-to-1 ratio. So the centroid divides each median that you've drawn into segments whose lengths are 2-to-1. That means if you just know the length of a median in a centroid, or in a triangle with a centroid, then you can actually figure this out without doing constructions or using your protractor. Example 1. Let's use some of these things. Find each length if G is the centroid of triangle PQR and the length PD is 15. So the length PD right there is 15. Well, the first thing we know is that this length will be 2/3. So for A, PG will equal 2/3 PD. If we substitute the 15 for PD, 2/3 15 will equal 10. So PG is 10. RG will equal 2 of FG. This is just another way of saying 2/3 and 1/3. So we know that FG is 3. they've given us the distance. So RG will equal 2 times FG, which 2 times 3 equals 6. Let's take a look at EG. EG is part of the median EQ, and QG is the longer piece, which is 2/3 EG, or 2 times EG. We can also state that EG would then be 1/2 of QG. So QG is 8, so 1/2 of 8 equals 4. So we're saying the same thing 3 different ways. An interesting thing about the centroid is the center of gravity of a triangle whose mass is uniformly distributed is located at its centroid. Such a triangle can be balanced at its centroid, and it would spin around this point if allowed to rotate freely. Another interesting thing about these triangles, if we had used equilateral triangles for all of these drawings, the Orthocenter, Incenter, Circumcenter, and Centroid would all be the same point. So your homework was lesson 5.1 and 5.2. 5.1 was numbers 1 through 7 and number 43 and 44. For 5.2, you had numbers 1 through 11 odd, and there's an extra credit problem, number 53. Even though we have demoed these in class, if you're still having difficulties and the websites don't work, please contact me for some assistance. God bless.